Hey everyone, so this is part 3 of camshafts and how you can help yourself by good information design better camshafts, or at least you're not. I'm not actually. It's really unrealistic to even think that you're going to design your own camshafts, but you're going to understand what the camshafts are doing and have some good general ideas of, wow, that camshaft is way off in your stuff, dude. At least in my opinion, or you can say stuff like that and speak from some intelligence. Okay, so what we're gonna do here is I'm gonna show you some stuff on the Cam Doctor real quick and show you acceleration rates and what the lobe is doing. I'll quickly explain the Cam Doctor. I'm not gonna bore you with actually doing a cam test, but you can basically see here. This is the Cam Doctor. This is the follower system, which sends everything to all the data information to the computer. So the camshaft turns just like this, and you can see that the stylus there, or the indicator, comes up, goes up the lobe, comes back down, follows that whole thing, sends all that information over to the computer. So let's go over to the computer. That's boring. Well, maybe a little bit neat, but it doesn't mean a whole lot. So let's go over here. So in one of our spring videos, we showed you the spring and with the spring tester and everything that's going on there. And now this has got the Cam Doctor information up here. Now I use the Cam Doctor basically, honestly, to see if I ever run across the camshaft that I don't know what it is, and it works really good, and I want to see what it is and see what's going on with it. That's fairly rare, but otherwise I'm always just kind of verifying what we have, what is in somebody else's engine if they don't know for sure, and I'll always be honest with people. If it's something that's really similar to what I would use, I'll tell them. So what I'll go over first is we've already gone over and I've talked to you about lobe designs and that asymmetrical lobe profile. Going to show you more about that and what this really looks like on the Cam Doctor, what it actually looks like in graph form, what the valve is actually seeing, which is really pretty interesting. So to get you, let's see here, this is the lobe. So just like you saw me turn the camshaft over here, this is the lobe profile. Alright, that's what the valve, what the lifter is actually moving. Alright, now, and there's some other things like valve jerk and the lobe jerk. That's really minimal in our type of camshafts and our type of profiles. And I'll explain more to you about that at the end here. But what you're seeing here, so that's our lobe profile. Normal, that looks good. Let me show you what the acceleration of the lobe looks like. So this is now blinking black. So this is how fast the lobe is actually accelerating. And we can get the actual numbers out here of where we're at. And I can chart all that out. But just to give you a quick graph information, you can see how fast that accelerates. And this is your major acceleration ramp right through here. Zero lift to basically about 50 to 100 right through there. That's your major. Actually, I'm sorry. Your major is 0 to 200, and then minor is 200 bucks. So you can see right here it accelerates real fast as it's just starting to open, and then actually as it's opening up through here, the acceleration drops down. Goes right up through there. Then as it's closing, remember us talking about the asymmetrical lobe profile? As it's closing right through here, now this camshaft actually isn't my camshaft, so it's a little bit interesting here. But you can see that that thing has got the same rate, same hump, closing and opening. So, and right up here at this peak lift area, and even at the last 200 thousandths of lift, it's pretty flat, pretty minimal. I think that little hump right there is actually a little, probably like a speck of dirt or some little deviation. Don't worry about that. But you can see as the camshaft, this accelerates really quickly through here. This is the lobe, not at the valve. I'll show you the valve in a second. Comes up, acceleration goes down, then comes back up as it starts closing the valve. But up here, this little sweet spot up here where the valve is open and air is a-flowing right through here. It's actually quite slow. And this is actually, this is a roller design. This is a solid roller deal. So your typical camshaft you're going to see out there. Let me see here. I think this thing with a 175 rocker on that core camshaft is like almost 900 lift right through here. Like I said, not my camshaft. But now let me bring up the valve, because motion at the valve is really interesting the way it actually does. So this is valve velocity. This is velocity of the cam, or actually the lifter. So this is what the lifter is doing. Next, I'm going to put up the because of the rocker arm ratio and what it does to the valve. You got to check this out. And let me see here. I think I got to change that. Hold on, because that's different than what it just was. Oh, I'm sorry, wrong one. There you go. Now you can see it here. So this little step right here is because we calculate in valve lash, and it goes boom, shoots right up, comes up. It's a multiple of an acceleration because of the ratio. So this is the actual lobe. This is the acceleration of the lifter. This is the acceleration of the valve. You see what's going on here? Then it comes down here, and because of the ratio, it actually slows down even further in velocity than what the lifter does. And then as it's closing, because this was not an asymmetrical profile, you can see it's very close to the same. And then this little drop off right here is basically, even though this is what the lobe profile looks like, this is what the valve is doing. Boom. Now when it comes down here, you see this thing flashing black. When it comes down here, it has a tendency to bounce. Now it's not exactly that sharp right there. I think there's a little bit of scaling issue there. I mean, obviously it can't quite go to that 90-degree point, but it's pretty darn close, and you get a really good comparison of what's going on there. So that's why we do that whole asymmetrical lobe profile. This is what's going on with your valve. It's accelerating very fast. If you're going to try to put a different set of rocker arms on, because you're going to figure out if it wants more camshaft or what it's doing, the camshaft lobe that is designed for a 1.7 rocker, and you put a 1.8 rocker on it, it is really accelerating fast. I mean, it isn't just picking up a little bit of lift, it is increasing this by a multiple of whatever. I mean, it is moving the valve fast and making things happen. Could be good, could be bad. You got to have valve spring and proper harmonics, or proper valve spring and pressures. A lot of things are going on there. Remember, we talked about push rods. Go back to some of those other videos. All of this stuff all fits together. Okay, everything has to work together. Perfect camshaft and crap valve train equals crap. Period. But anyways, so if you want to try putting $1,500, $2,000 worth of rocker arms instead of changing the camshaft, that's fine. But just remember, it's not a direct comparison, and you're not just picking up lift. You're picking up a lot of acceleration. Things are opening and closing. The ramps are much faster, and things, the little bit of lift you're gaining is nothing. That doesn't matter. What's happening is all this area here and all this area here. So that is what is going on with the camshaft and what's going on with the profiles. So what everybody wants to know, how do I pick out the right camshaft for my engine? Now, since there are about 1 million different engine combinations out there, I can't tell you how to pick out the right one for yours, but I build boosted engines. That is what we do here at Steve Morris Engines. NA is going to be different. Okay, so in general, your camshaft you're thinking about is probably too big. In general, it's probably too big. Now, in an NA deal, everybody really overcams NA stuff too. In order to have the kind of camshaft that most people think they need, you really need to have a lot of engine, and a lot of other things have to go along with it to capitalize on that. Otherwise, it's just a bunch of pumping losses. But Since we do boosted stuff, I'm here to tell you this is the number one thing you need to understand about selecting a camshaft for your engine. The number one thing is it's not NA. Our power limitation, our air limitation is in your power adder. That is the number one thing. We're not building a camshaft for maximum engine power NA because you have a blower on it or you have turbos on it. You need to, the camshafts need to be designed and need to be built and made for boost, for controlling the air pump. The air, let's see, your engine is an air pump, but your air pump is being fed by air pump, basically. In the boosted world, that's all I care about. So in the boosted world, we need to build our camshafts based on what blower is in there. So, for example, I have a customer here that sent in a engine for a conversion, and it was a turbo motor. He wants to just put it was a NA motor, and he wants to put a small blower on this. So we're going to put this F1A 94 blower on it. I think we might even step it up just maybe to the F2, but he wants a small blower, wants to make a little bit of horsepower on a 632. The problem is a 632 moves a lot of air and will eat up that blower. Go back to the blower videos. I talk about what is going on with the parasitic drive losses, all of those other things. So your camshaft has to be designed, and you need to think about your camshaft according to the blower that's on it. What will happen is if I put the normal 632 camshaft in it, let's say that normal camshaft is going to be like probably 280s at 50 on the intake and 296 to 300 on the exhaust at 50, and it'll have a 475 to 475 to 500 lobe. So 500 lobe times 1.7, you can figure out the math on there. That would be pretty normal camshaft lobe duration numbers. All of our, let me backtrack just a little bit. All of our boosted stuff is going to be somewhere in the neighborhood of 114 to 118 degrees of lobe separation. We'll go out a little bit farther on turbo stuff and usually narrower on the supercharged stuff. I'll explain that in a little bit. But let's go back to the reason why we need to look at what camshaft we'd have in this great big motor. So this great big engine, if I put that camshaft in it, it is really moving a lot of air. It's a pretty big pump. The pump that we're feeding the pump with is really small. It's a limited blower. I need to take a lot of camshaft out of this motor in order to make it be efficient as much as possible with the blower. The blower is the issue. It has a small blower, great big motor. That's why you're always going to see in the boosted world, big cubic inch stuff is hard to make work. There's a couple different reasons for that, but this is one of them. Is that they usually run the compressors right off of the map, right out of efficiency. So I have now taken this camshaft that I normally be in the 280s and 300s, high 280s, 300, and have gone down about 20 degrees of time, or I'm sorry, 20 degrees of duration at 50. So what that's going to do is I'm tailoring this engine, I'm tricking the engine into thinking it's smaller so I can utilize the boost and the blower size. Because what we need to do is we can't just make maximum power at 5,000 RPM. That's useless in most applications, and that's what would happen if we ran that great big cam. It runs that the blower is the air pump feeding the air pump. It doesn't matter how good you make the primary air pump, that power adder air pump is it. You're not sucking air through it like an NA motor. It's taking air, it's going to take horsepower to drive it, it's going to have some type of pumping losses, there's compressor maps, there is efficiencies, a lot of stuff going on there. So you need to, in this application, I needed to really make the camshaft small. fact, it's a little bit smaller than what I would normally put like in the 540 with the same blower. All trying to make this thing a little bit happier with this big cubic inch motor. So if you are limited in blower size or turbo size, then you're going to have smaller camshafts. Your lobe separations always stay about the same. I usually never change that. Like I said, the turbo stuff being 1/16, 17, 18. And we talked earlier in one of the other videos about the negative offset that's applied in our camshafts, so that's why they're already have a retard that's already ground into them. So we won't go back and cover that. If you want to see it, you just need to go back and read that or listen to that video. So we always want to keep that in that same range, so that doesn't change a whole lot. We widen out that lobe separation to take away a little bit of overlap and try to control some of the back pressure issues, especially in turbos. So in the turbo motor, that's why it's 1/16, 17, 18 degrees of lobe separation, because as we increase the lobe size, naturally our lobe size, you know, we have another lobe that's right over here, our overlap increases as the lobes get bigger. So like your typical stockish LS kind of deal has negative overlap, has none, has zero overlap. Typical like a big inch motor or something around there will have anywhere from 20 to 50, 60 degrees of overlap in an NA deal. Our stuff will have somewhere in the neighborhood of somewhere in the range of in the 20s to 30s because I like to use the smaller lobe, because we're not trying to make maximum horsepower with the motor. We're trying to make maximum horsepower with the blower or the turbos. It is a different deal. So always look at you're always going to be in that 114 to 116 on blowers, 116 to 118 lobe separation on turbo stuff, and that's just for some back pressure issues, and we're trying to control our overlap. Then so we don't have so much blow through. Makes back pressure on turbo stuff and on a supercharged stuff with something that has too much overlap, that has like 110 or 112 degrees of lobe separation and has a bunch of overlap. It actually will try to send a fair amount of raw fuel out the pipe, out the exhaust pipe. It skews your O2 and your EGT readings. You think it's rich when it's actually lean, so you end up taking more fuel away from it and ends up losing horsepower. So there's some things there of trying to make sure that it is running, using the fuel that it has there. And that kind of stuff you can't change with just the tune-up, because it's a mechanical valve opening up, closing, opening up, and closing the exhaust. So a bunch of overlap, too tight a lobe separation really kind of messes that stuff up. So that's why we like to have that wider. Then what you'd want to do for all of these engines, in general, I don't have anything any bigger than let's see here, 270s at 50 in any LS deal, and that is 2500 horsepower LS stuff. So that'd be like a mid 270s at 50 and mid 280s, that almost 290. That's a pretty big camshaft in a big cubic inch LS, 427 cubic inch LS, something that'll make 2500 horsepower or more. The big stuff, I mean, even my biggest engine there, you know, it's, like my SMX stuff, it's making 4500 plus horsepower and proven out, and that thing only has that is a 280. These aren't the exact numbers, but it's like 280, 281 on the exhaust. Not much split there because it has really good exhaust on it. Also has I don't need to overcome anything there. So a much larger exhaust lobe in a unlimited type engine like that tends to over scavenge. So what I'm trying to get at is smaller motor, will always have smaller camshafts. 540 cubic inch motor stuff, a really good killer camshaft in an unlimited blower situation, so big F3 stuff or unlimited turbo stuff is going to be fairly big. It's going to be in the range, at least fairly big in my interpretation, anywhere from the high 270s on the intake to high 280s on the intake, and usually about a 10-degree spread, 10 to 12 degree spread. That on big block Chevrolet stuff, because that's just supercharged. There's always a 10-12 degree spread on a supercharger because we need to get rid of some of that exhaust gas. On turbo camshafts, they're always a little bit closer, usually not quite as much spread on a turbo camshaft, unless it has an exhaust problem, bad exhaust port, small exhaust valve, something like that. So that's why it's so hard to just give a random generalities, unless we went over a generality for every type of engine, every type of combination, which is really, really tough. But in general, you probably have too much camshaft in it. Step it down, be in the in a more reasonable range, and let's cover lift here. So basically covered up your duration, basically covered up your lobe separation. So let's go to that lift. Alright, sorry about that. I had to get the screen back to it. So going back to lift. So I said in a previous video, I mean, if you're automatically just talking about lift, you're not really understanding the full picture. What I really am trying to get lift to do is, lift is basically to smooth out and make our valve velocity and our lobe velocity tolerable, so we can get our lift area so the valve is open. So it's not our goal. It's not, oh, I need to have 700 lift, I need to have 800 lift, 900 lift. My heads flow max at 900 lift. I don't care. It does not matter. Why does it not matter? It does not matter because we are building the engine and the camshaft profile based on what the feeder air pump is, not what the main air pump is. The power adder air pump is what we have to be concerned about. So we don't need a ton of lift trying to get, there's actually a thing called inertia supercharge effect, and that is air moving through the cylinder and out the exhaust actually pulls in air, etc., etc. That's all NA stuff. That doesn't happen in boosted world. Obviously, we're at positive pressure on the intake side, and always more positive pressure on the intake side than the exhaust side, even in turbo stuff. If you don't, you got big problems. But anyways, we don't need all that lift. We need a smoother, calmer profile, because we're not trying to get that inertia supercharge effect. We're not trying to make this thing the maximum NA camshaft possible. We are trying to match everything to what blower is on this. Remember, limited blowers are always going to be smaller camshafts than the unlimited blowers. And as the engine size goes up, so will obviously the camshaft size. That's why I did the core sizes, what that does to the lift, or what that does to the valve motion. It does change this valve motion some with a larger journal and a larger lifter. That's why we need to enter in the lifter information into the computer for it to calculate these things out properly. But would like to have, my biggest, the biggest lift, I told you in the last video, we're only in the 860s, 870s on something that makes upwards of close to 5,000 horsepower in the boosted world, not NA. NA stuff, I know there's got, mountain motor stuff, 800 plus cubic inch kind of deals. They'll have upward, over an inch lift, over like an inch 0.2 lift, sometimes a little bit bigger. Man, that is really hard on parts, but totally unnecessary and is detrimental in the boosted world. So if you're like I said, going back to it, let's say your heads flow the most at 900 lift. Well, okay, but we're still going to be building that camshaft to the blower or the turbos that you have onto it. And it's never going to be, I don't need to get the valve up in that lift range in order to utilize the head, because this is not a NA deal. Can't stress that enough. That is what the biggest difference of what we're doing is. It's not NA. It doesn't need to have all that camshaft. It doesn't need to kill valve train parts. It doesn't need to do all that kind of stuff. It just needs to feed. Let the boost power adder pump feed the main engine air pump. So always just kind of remember that. So don't worry about that big lift and always trying to be, get it up, your valve lift up to your airflow numbers and all that other stuff. Don't worry about it. We'd rather have good low lift numbers anyways, and we could, right when it's right in this sweet spot in this area at 200 to 200 basically to your peak lift is a really sweet spot of where it has the most area open on the valve. It's really getting the most effect through there. Adding another 50 thousandths a peak right here just doesn't do anything, because in the grand scheme of how much it changes this area, when you just change this, is really, really minimal. So always remember that the lift really doesn't matter. You're probably too big on camshaft. You're probably too big on lift for sure. Don't worry about the rocker arm ratio, because rocker arm ratios are really dictated by how the camshaft's designed. That's why I ask you what rocker arm ratio you got. Can you put like go from a 1.5 to 1.6 in like street rod stuff? It's not the end of the world, because it'll usually absorb that. But as we continue to go up and up and up in big power stuff, you can't. Well, you heard my dog barking there. That means it's time to go. He's still barking. He wants to go home. He's hungry. It's late. So, anyways, just recapping that for you. Don't worry about the lift and those things. You were really trying to build this camshaft, probably smaller than what you're thinking. And the whole reason why we're doing this video series, and because I can't feed you every single bit of information, is that if you're watching this, you're part of Steve Tech, you have a question about your specific camshaft, I'm more than happy to design it for you, and I tell you what's going on with it. If you have a camshaft that you are questioning, I am more than happy, if you're a Steve Tech member, to help you with it. And that's how I'm giving you these big general things and big general ideas, because I can't go over every single detail for every single combination that everybody has on a video. But you're more than welcome to shoot me an email, give us a call. More than happy to help you out if you have a camshaft and you have a question about it. I will tell you, yeah, you're pretty close, and you mean that's not a real big deal, or I could do a camshaft for you and it'll make you another 50 horsepower, 100 horsepower, no horsepower. I'm more than happy to tell you that. There's a lot of times that people have some really close camshafts that it's not worth spending money on it, and I'm more than happy to tell you that too. So anyways, I hope you guys have enjoyed this. If you do have any comments, like I said, I'm really sorry. It's just so much to go over for everybody's combination, but this is how things work, and it's a series, and everything works together. So remember, works together. The blower, and you're building the engine and tuning engines and designing engine parts and camshafts based on what the power adder is, in combination with the motor, to make them work efficiently together. So anyways, I'm Steve Morris, Steve Tech. Have a great day.